Welcome. Today we will look at the atomic physics. The rules here are very strange and different from our everyday life. We will learn about a big mystery of nature, theory. So what actually happens when a wall weighs less than its part? Image you build a Lego house with 20 blocks. The finished house weight is the same as the 20 loose blocks. That's normal, but atoms are different. A finished atom weighs less than the parts used to build it. The whole literally weighs less than the sum of its parts. The whole atoms weight less than its parts. This is very unusual. To really picture this bizarre phenomenon, physics how this mass defect image a skull on one side. You have 6 separate protons and 6 separate neutrons on the other sides. You have a carbon 20 nucleus made of those exact same 20 particles. The separate particles weigh more than the finished nucleus, so mass is gone. A literal fraction of the mass has just vanished. A small part of the mass disappeared when the nucleus is formed. Okay, so where on the Earth did that missing mass go? Where did that mass go? Einstein's formula E equals 2 mc quadrat explain it. Mass and energy are two sides of the same coin. Mass can change into energy. The missing mass changed into binding energy to hold the nucleus together. I got converted into the incredible intense energy. It changed into the strong energy that's necessary to hold the nucleus together. To really wrap our heads around the massive scale. In the formula, c is the speed of light. Because the speed of light is huge, a tiny bit of mass creates a giant amount of energy. This process powers our sun by turning hydrogen into helium. It's the same physics driving fusion. This same rule works in nuclear power plant, nuclear weapons and physics experiments. Before we go too deep into the mechanics, let's explain standard physics notation. X, the chemical symbol of the element. A, the total number of protons and neutrons together. Z, the number of protons. This shows what element it is. And that what ultimately definite which element is actually is. The number of protons tell us exactly which element it is. Alright, so how do you actually find this mysterious mass defect? Finding the mass defect is easy subtraction. Add the mass of our separate protons and neutrons together, subtract the real mass of the finished nucleus. The small difference left over is the mass defect, and as just so, that's tiny fraction of mass. That tiny bit of missing mass is that main source of power in the universe, which bring us to a really important term. Making a nucleus releases energy, so it is an exothermic reactions. To break a nucleus apart, you must put energy back in. This called binding energy. This energy is so. This energy is much bigger than normal chemical energy. Reactions. Those deal with the tiny binding energy. Chemical reactions use small electron energy. Nuclear reactions use the giant energy inside the nucleus. Let's look at specific number to ground this. Iron 56 has a binding energy of 8.7 mega electron volts per nucleon per particles. We divide the total energy by the number of particles and compare different atoms fairly. That gives us really solid average. This knows the average energy holding each individual proton and neutron place, and that calculation bring us to this. This graph is very important. It is map of stability. The vertical line shows energy per particles and the horizontal line shows the number of particles. A higher position on the curve means more stability. The higher up on the graph a nucleus sits, higher up means more binding energy and better stability. Now take a look at the absolute peak of that curve. Iron 56 sits at very top. It is the most stable element in the universe because nature loves stability. Other elements want to turn into iron-taught nuclear reactions. But before we talk about how elements try to become iron, the start of the curve has sharp spikes. There are extra stable small element helium-4 is a famous example, carbon 20 and oxygen 16 also spike because they are like groups of helium nuclei joined together. Alright, let's zoom out and look at the broader picture. Let's compare the two sides of the graph. The left side light elements goes up very fast. The right side heavy elements slowly goes down because too much positive protons push each other away, making the atom unstable, making those heavier increasingly unstable. This push makes heavy nuclei less stable. So that steep left side of the graph, the left side is for nuclear fusion when two light elements join to make a heavier one. They jump off the curve. This creates a huge mass defect and releases massive energy. This process powers the stars. This exact process specifically fusing hydrogen into helium makes the light and heat that allow life on Earth. So you are probably thinking, if it creates so much energy, we use fusion on energy because it is very hard. Protons repel each other. The strong nucleus force only works when they are extremely close. To make them touch, we need extreme heat, like the center of a star. Essential. You literally have to create the core of a star. We have to make a tiny star right here on the Earth. Because fusion is identified difficult power of today we use nuclear fusion. Heavy unstable atoms like uranium are split into smaller pieces. The smaller pieces move leftover iron on the graph and releases a lot of energy. And just like with fusion, this move towards stability, moving towards stability creates a mass defect and releases a large amount of energy. But here is kicker. Here is important part. Fusion rarely just happens once. Fusion causes a chain reaction. One neutron splits uranium atom which releases two or three new neutrons. These neutrons split more atoms in reactions in a reactor. We control this for electricity. Uncontrolled, it creates a nuclear bomb. But when it's uncontrolled, it results in the devastating releases. Uncontrolled, it creates a very dangerous nuclear explosion. Let's summarize this epic cosmic contrast. Summary. Fusion joins light atoms, power stars, and gives massive energy, but need extreme heat. Fusion splits heavy atoms, power electricity, plant gives less energy, and needs carefully control. It powers our easily power station. Um, Fusion runs power station gives a bit less energy, and the big challenge is controlling the chain reactions, which leaves us looking at the truly thrilling frontier. Today, scientists are trying to create controlled fusion on the Earth using types of hydrogen called deuterium and tritium. If they succeed, we will have limitless clean energy from a tiny mass defect. It is a beautiful reminder that the great secrets are hidden in things we cannot see. Thank you for listening, keep learning, and see you next time.